Sir, you are muted.
Yes, sir. You are not audible, sir.
Am I audible now?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so I said that in the previous example, x3 and x4, these are free variables, and the remaining variables, x1, x2, x5, these are basic variables. Okay, so these 2 points. So now we move to the next topic. I think this example is also pretty much obvious, related to the rank and the system of equations. So I leave this example for you to read. So basically in this example, you have two unknowns, lambda and mu. So you have to you have to find the values of lambda and mu, for which you don't get any solution, the values for which you get unique solution, and values for which you get infinitely many solutions. Okay, so the same type of argument you have to adapt. You have this augmented matrix, which you can write in this form, and then you use elementary row operations, some elementary row operations, to reduce this to this matrix, and from there you have to identify the values of lambda and mu in these three cases. For example, for the unique solution, for the unique solution, the rank of the augmented matrix, the rank of the matrix A should be equal, and this should be equal to the number of variables. Okay, so basically you have to look at this last row and identify the values of lambda and mu, so that the rank of A is equal to the rank of the augmented matrix, and this is equal to the number of variables, which is 3 in this case. Okay, so you can read all these points already written here, and then you have some couple of more exercises, so that also you can try at home. So homework and some quiz questions. Okay, so now we move to the next topic, which is special type of matrices. Here we are going to see several type of matrices. For example, symmetric matrix, skew symmetric matrix. Then we will see orthogonal matrix, and another is normal matrix, and then some complex matrices. And in the complex matrix, we are going to see Hermitian matrix and skew Hermitian matrix. And the corresponding real part of this is symmetric and skew symmetric matrix. The real part of the Hermitian matrix is symmetric matrix, and the real part of skew Hermitian matrix is skew symmetric matrix. And then that will conclude this section, and then we will move to eigenvalues and eigenvectors, which is a very interesting topic. So let us see the definitions one by one. Along with the definition, we will also see some properties of these matrices. So first definition is symmetric matrix. So consider a square matrix of order n. We say that matrix A is symmetric if the transpose of A is equal to is equal to the matrix A. This means that the Aij element of matrix A, this is I jth element of matrix A, is same as the jith element of A for each I and j varying from 1 to n. So if this happens, then we can say that the matrix is symmetric. For example, if you consider this matrix written on the slide, we can easily see that the transpose of A is A, or you can check that Aij is equal to Aji for each I and j. Right. So when we say that transpose of A is equal to A, this means that the first row of A will be the first column of first row of A will be the first column of the transpose, and so on. Second, first, second, third, and so on. Okay. So, but if you consider this relationship Aij is equal to Aji, so you can clearly see that this is A21. No, this is A12. A12 should be equal to A21. Okay, they are same. This is A13. A13 should be equal to A31. Okay, so they are same. Then this is diagonal elements. So diagonal elements are not going to change. Aij is equal to Aij. This is A23. A23 should be equal to A32. A32 is this. Okay. So this is a symmetric matrix. In this way, you can check the entries, and you can say that this is a symmetric matrix. Okay. Now, the another type of matrix is a skew symmetric matrix. We say that a square matrix of order n is skew symmetric if Aij is equal to Aj minus of Aji. And here you can see that the matrix B on the slide is skew symmetric. For example, this is element A 1, 2, and if you take the negative of this, you get A21. So A21 or A12, A21 is equal to minus of A12, or you can say that A12 is equal to minus of A21. Similarly, you have this is the first element in the third element in the first row, and negative of this is minus is A31. So A31 is equal to minus A13. Okay. Similarly, you can see this 2 is A. This is the third element in the second row. So A23. A23 is equal to A minus of A32. Okay. So and the diagonal elements will be 0. In this case, the reason is that if this relationship hold, Aij is equal to minus of Aji, and if you put j is equal to I, in this relationship, we take j is equal to I, then you have Aii is equal to minus of Aii, and this happens only when Aii is equal to 0. Okay, so this means that the diagonal element of the skew symmetric matrix, all the diagonal elements are 0. Okay. So this is what we mean by symmetric matrix and skew symmetric matrix. Yes. Any question? Okay, so in other words, we can say that A transpose is equal to minus of A. Okay, so we say that the matrix is symmetric matrix if A transpose is equal to A, and matrix is skew symmetric matrix if A transpose is equal to minus A. Fine. Now we have some properties here. The first one says that for any square matrix A plus A transpose is symmetric. This can be proved easily. Now to prove this, we can calculate the transpose. So we have A plus A transpose. This is my matrix, and I take the transpose of this. So this will be A transpose plus A transpose transpose. Then you have A transpose. A transpose transpose is A. Because A is symmetric matrix, so we can say that this means that yeah, so from here we get that A plus A transpose of this is equal to A plus A transpose. So from here we can say that A plus A transpose is a symmetric matrix.
Sir,
Yes,
here A can be any matrix. I mean symmetric or skew symmetric.
any matrix,
Okay, sir.
any square matrix. Okay. And the second one is A minus A transpose is skew symmetric. So you have A minus A transpose. You take the transpose of this, you get A transpose minus A transpose of this. You have A transpose minus A, which you can write as minus of A minus A transpose. So from here we get A minus A transpose of this is equal to minus of A minus A transpose. This means that A minus A transpose is skew symmetric. Okay. Now the second property, sum of two symmetric matrices. So let me erase this first. Now this property says that sum of two symmetric matrices is also symmetric. So let us say that I have a matrix A. This is symmetric, and another matrix B, and this is symmetric. A and B are both symmetric matrices. Then this result says that if I take the sum of these two matrices, then this is also symmetric. So I can calculate A plus B transpose. This will be equal to A transpose plus B transpose, but A and B are symmetric. So A transpose will be equal to A and B transpose will be equal to B. So from here we can conclude that A plus B is a symmetric matrix. Fine. Now the second part of this is if I take two skew symmetric matrices, then the sum is a skew symmetric matrix. So we just modify this. So let us say that I have a matrix A as a skew symmetric. So that means A transpose is equal to minus A and B transpose is equal to minus B. So you can again start from A plus B transpose. This will be equal to A transpose plus B transpose. But A is a skew symmetric matrix, so A transpose will be equal to minus A. And similarly, B transpose will be equal to minus B. Okay, so from here we get A plus B transpose is equal to minus of A plus B. So we can say that A plus B is a skew symmetric matrix. Okay, so first point, second point also we have done. Now let us go to the third one. A is symmetric, then constant time A is asymmetric matrix. And if A is skew symmetric, then constant time A is skew symmetric. Okay, so this is also very easy to prove. Let me erase this and then can write the proof here. So first case is, let us say that A is symmetric, and then we want to show that K into A, where K is not equal to 0, is a symmetric matrix. So A is symmetric means A transpose is equal to A. Now we consider K times A, where K is not 0. Okay, so K A transpose, this will be equal to K A transpose, but A transpose is A because A is symmetric matrix, so we can write this as K A. Okay, so from here we can conclude that, from here we can say that Ka is a symmetric matrix. Now the second part of this point is A is skew symmetric, and we want to show that K into A is skew symmetric. So now in the second part, A is skew symmetric. That means A transpose is equal to minus A. So K into A transpose is equal to K A transpose. But A transpose is minus A, so this is equal to minus Ka. And then we can say that Ka is a skew symmetric matrix. Fine. No problem. Now let us go to the next part. It says that A and B are symmetric matrices of the same order. So that means A is symmetric. This means A transpose is equal to A. And B is also symmetric. That means B transpose is equal to B. Then AB is symmetric if and only if AB is equal to BA. Okay. So we can start from by taking a transpose of the product AB. Right. So this is equal to B transpose A transpose, but B transpose is B and A transpose is A. Okay. And this is equal to AB. Right. So from here we can say that AB is a symmetric matrix. Right. So if I assume that AB is equal to BA, then I can show that AB is a symmetric matrix which I have written here. The proof of this I have written here. And conversely, if we assume that AB is a symmetric matrix, then this is possible only if AB is equal to BA. Okay, so you can just proceed in the reverse direction. That means you can say that AB is a symmetric matrix. That means AB transpose is equal to AB. And then AB transpose can be written as B transpose A transpose. And since A and B are symmetric, so you get B, this is equal to BA. And this is only possible. And this means that this shows that BA is equal to AB. So both ways you can prove. So first, we assume that AB is equal to BA, and then show that AB is a symmetric matrix. Conversely, we assume that AB is a symmetric matrix, and then one can show that AB is equal to BA. Okay? So this proof is also very simple. Now the next part of this this question says that A raised to P is a symmetric matrix for any positive power P. And this is very much obvious, because if I take A is equal to B or B is equal to A, then from this result we can say that this AB will become A square. So A square is symmetric if and only if A square is equal to B square. If you put B is equal to A in this relationship, when this is true. So immediately you get that A square is a symmetric matrix. And once A square is symmetric, you can say that A square is another matrix. That means you apply the same result again by taking A as A square and B as A to say that A raised to 3 is a symmetric matrix. And then you repeat this again to show that for any positive integer P, A raised to P is a symmetric matrix. Okay, so this is also quite straightforward.
Sir,
Yes.
sir, will you please repeat this A to the power P is symmetric concept, please, sir?
Yeah, sure. So just now we have proved that AB is symmetric if this condition is satisfied, and this holds for any symmetric matrix, right? So if I take any symmetric matrices B and A, so if I take B is equal to A in this relationship, this will become A square, and this relationship will become A square is equal to A square, which holds trivially. This holds trivially. And if this holds, then we can say that AB is symmetric. AB is symmetric means A square is symmetric. So from here we get that A square is symmetric. Up to now this is fine.
Yes, sir.
Right. So now you repeat the argument. Now what you do is you replace this A by A square, and take this B as A. So what do you get? This product. This product becomes A raised to 3. And this relationship will again hold trivially, because this is again A raised to 3 is equal to A raised to 3. So this holds trivially. So from here you get A raised to 3 is symmetric. Fine?
Yes, sir. Fine.
And then you repeat this. So you can apply the inductive argument. You can say that A raised to K is symmetric. And since A raised to K is symmetric, so what you can do is you can take A, you can use this relationship again by taking A as A raised to K and B as A. So this relationship will hold automatically, because this is A raised to K plus 1, A raised to K plus 1 holds trivially. Okay, but here this product will become A raised to k plus 1. And from this result, directly you can get this is a symmetric matrix. Is this fine?
Yes, sir.
Yeah. So that is why you get a raised to p, a raised to p is symmetric for any positive integer of p. All right. Any more question? So no more questions, then we can go to the next property. So it says that B transpose AB is symmetric and or skew symmetric if A is symmetric or skew symmetric. So here, when A is symmetric, then B transpose AB is symmetric. And the second part of this statement is that if A is skew symmetric, then B transpose AB is skew symmetric. Okay. So I think this is not complicated at all. I will just show the symmetric part. Skew symmetric part you can easily see. So B transpose AB, I want to show that this is a symmetric matrix. So that means I take the transpose of this. So this will be equal to B transpose, A transpose, B transpose, transpose. And this is equal to B transpose. Okay. A is symmetric matrix. That means A transpose that we have here in the product, this will become A, and B transpose will become B. Okay, so from here we can say that B transpose AB is a symmetric matrix. Fine. For the skew symmetric matrix, when you replace A transpose, this will be replaced by, instead of this A, you will write minus A here. And you can see that this is equal to minus of B transpose AB, which means B transpose AB is a skew symmetric matrix. Fine. Okay, so rest of the properties I think is more or less similar. I do not want to repeat the same argument again and again. So you can check that if A is a skew symmetric matrix, then A raised to 2k is a symmetric matrix. You can see that this is a even power of a even power, and the odd power of A is skew symmetric for any integer k, any positive integer k. So if A is skew symmetric matrix, then A raised to 2k is symmetric, and A raised to 2k minus 1 is skew symmetric. Okay, you can easily check by taking the transpose and all those things. You can easily check. Now the next one is A and B are symmetric matrices. Then AB plus BA is symmetric, and AB minus BA is skew symmetric. This is also very easy. You just take the transpose here, use the fact that A and B are symmetric matrices, use the property of the transpose, and then you get this immediately. Okay, so nothing special about these statements. All these statements can be proved very easily. So I leave this for you to try at home. Now the next property is, this says that any square matrix can be expressed as the sum of a symmetric matrix and a skew symmetric matrix. Okay, so if you take a square matrix A, you can write this square matrix as A plus A transpose divided by 2 plus A minus A transpose divided by 2. Fine. A transpose by 2 cancels out, and A by 2 plus A by 2 will give you A. Okay, so this relationship holds for any square matrix. Now you can easily show that this is a symmetric matrix. A plus A transpose by 2 is a symmetric matrix, and A minus A transpose is a skew symmetric matrix. Okay, so let us see how this is true. So you have A plus A transpose divided by 2. You take the transpose of this. 1 by 2 is out. You have A transpose plus A transpose of this, which is equal to 1 by 2 A transpose plus A. So this shows that A plus A transpose by 2 is a symmetric matrix. And similarly, you can show that A minus A transpose by 2 is a skew symmetric matrix. Okay, so this is also an easy exercise, last property. Fine. So any question in this section on skew symmetric matrices and symmetric matrices?
Sir, why determinant of odd ordered skew symmetric matrix is 0?
Determinant of
Odd order skew symmetric matrix.
odd order skew symmetric matrix
Is 0.
If you have A transpose is equal to A, you take the
And it can be proven by that relation A equal to minus A transpose.
Yes, sir. If you take both side determinant, -1 cells
Yeah.
have odd order. Its odd power will be -1, and 2 times the determinant will become 0, and determinant will be 0.
yeah.
Yes.
Yes, sir. Got it. Got it. Thank
Yeah.
you, Chir.
Any more question? Okay, so now we move to the next definition. You have, let us say, a vector u. The components of the vector are u1, u2, so on to un. Another vector v. The component of this vector are v1, v2, vn. And this is a vector in Rn, because we have n components in each of these vectors. So these vectors are said to be orthogonal. They are said to be orthogonal if the inner product of u and v, which is defined as u into v transpose, and u into v transpose is u1 into v1 plus u2 into v2, so on to un into vn. This is equal to 0. If this happens, then we say that the vectors u and v are orthogonal. Okay. Now we have a set of vectors. So whenever you see u1 in the bold, you see that you have u1, u2, um in bold letters. U is in u here in all the expression are in bold letters. In this expression, u is not in bold letter. So if u is not in bold letter, that means this denotes the component of the vector. If it is in bold letter, then this denotes the vector. Okay. So we have set of vectors u1, u2, so on to um. These are m vectors in Rn. These m vectors are said to be orthogonal. Earlier we had two vectors u and v, and we said that two vectors are orthogonal if the inner product is 0. This is known as inner product or dot product. Okay, this is 0. So we first define the orthogonality of two vectors. Now we are defining the orthogonality of m vectors in Rm. So they are said to be orthogonal if for any I and j, not where I and j are different, u into j is equal to 0. Okay, so if whenever I and j are different, the inner product or the dot product of ith vector and the jth vector is 0. Then we can say that u1, u2, um are orthogonal vectors. We can say that these vectors are orthonormal if the inner product, if they are orthogonal. First of all, they are orthogonal. That means if I and j are different, then the dot product of ui and uj is 0. And whenever I and j are equal, the dot product is 1. Then we say that they are orthonormal. Okay, so here we saw two definitions. One is orthogonal and the other one is orthonormal. The only difference between these definitions, yeah.
ऑर्थोनॉर्मल एक और बार बता दीजिए सर.
So orthonormal means इसमें एक एक्स्ट्रा कंडीशन ऐड कर दो. ये तो ऑर्थोगोनल था ही. जब आई एंड जे इक्वल नहीं है तो इनर प्रोडक्ट 0 है, डॉट प्रोडक्ट 0 है. और एक साथ में एक्स्ट्रा कंडीशन और लगा दी कि जब आई एंड जे इक्वल है तो इनर प्रोडक्ट 1 है. इसमें ऑर्थोगोनल में ये कंडीशन नहीं था, लास्ट वाला. तो ऑर्थोगोनल में अगर तुम्हारा जे इक्वल भी है तो जरूरी नहीं है कि वो 1 हो सकता है कि वो कोई दूसरा एक्सप्रेशन हो अदर देन 1. So if this is 1, then we say that this is orthonormal.
सर अगर यूनिट वेक्टर्स होंगे तो ही ऑर्थोनॉर्मल बोलता है कि कोई और केस भी है?
Sorry, say again.
If they are unit vectors, only then we put the orthonormal name, or there is another condition also.
No. So orthonormal means you have unit vectors and they are orthogonal.
Okay.
Okay. So this is denoted by the length of the vector, u1 squared, u2 squared, so on to un squared, and under root. The notation for the length is this. If you learn higher mathematics, then this is known as norm of u, the Euclidean norm of u. Okay, so for the time being, you just consider this as the length of the vector.
So what is it called? Can you repeat it again?
Which one?
So this length of vector.
This length of vector is also is known as norm. Norm.
Okay, sir.
Norm means you have to learn some higher a course on a higher mathematics course. Then you will know what is norm. So just consider this as the length of the vector. Okay.
Okay, sir.
Now we define what is orthogonal matrix. So we say that a real square matrix is said to be orthogonal if A inverse is equal to A transpose. In other words, we can say that A into A transpose is equal to I, or A transpose A is equal to I. So from here, we can say that the rows of A are orthonormal vectors. So basically, when you take the transpose, you have a matrix A. And when you take the transpose, the rows will become column in the transpose. And when you multiply A by A transpose, that means you are multiplying the first row by the first row, first row by the second row, third row by the first row by the third row. Similarly, second row by the first row, second row by the second row, second row by the third row, and so on. Okay. So the product is equal to I. That means if you multiply the first row by the first row, you get 1. If you multiply first row by the second row, you get 0. Okay. So from here, from the definition itself, we can say that the rows of A are orthonormal vectors. And we have an example of the orthogonal matrix. So you have this matrix A. Now you calculate, first of all, you calculate A transpose. A transpose will be this. This is your first row. This first row will become the first column in A transpose. The second row of A will become the second column of A transpose. And the third row of A will become the third column of A transpose. Okay. And then you multiply them. And this is your A. This is your A transpose. You multiply them, usual matrix multiplication, and you get the identity matrix. Okay, so we can say that this is an orthogonal matrix. In general, we can say that if I have a matrix A, let's say I have a matrix A, let's say A11, so on to A1n, A21, A2n, AN1, ANN. Now let us say that the first row of A, I denote this first row of A by U1. So you have U1 here. The second row of A is denoted by, let's say, the vector U2. So you have U2 here. And the nth row of A is denoted by UN. So you have the vector UN. Fine. So this is your matrix A. Matrix A consists of the vectors, the row vectors U1, U2, UN. I think there is one typing mistake again. So it should be A into A transpose. Now in A transpose, the first row of A will become the first column of A transpose. So A transpose will be U1, U2, UN. And then you multiply them, so you get this matrix. And we say that for this matrix to be orthogonal, we said that this should be equal to the identity matrix, which is this one. So if you start comparing the component wise, all the diagonal elements are 1. So here the diagonal elements, these are the diagonal elements. So you can say that U1 square plus U2 square, so on to UN square, all of them are 1. And the off diagonal elements, these are off diagonal elements. These are off diagonal elements. That means U1 into Uj, whenever I and j are not equal to 0, I and j are not equal, U into j is equal to 0. Okay, so this is from here we can show that the rows of A are orthogonal. Now, instead of taking the rows, if you take the columns, then also you can say that the columns are also orthogonal. So similarly, we can say that columns of A are also orthogonal. And the proof is pretty much similar, because you can write A as instead of writing U1, U2, UN, you can write the columns of A. Okay, so you have this, let's say, C1 first column, C2 second column, C3 third column, Cn nth column, and then you can write A transpose as C1, C2, Cn. The first column of A will become the first row of A transpose. Second column of A will become the second row of A transpose, and so on. And then you multiply, equate this to the identity matrix, and then compare the product A into A transpose with the identity matrix component wise. So you can see that the columns of A are also orthonormal. Is it fine?
Yes, sir.
Yeah. So any question here? So no questions, then we move to the next slide. So immediately, just now we have seen that we can conclude that the three statements are equivalent. If we say that A is orthogonal, then this is equivalent to saying that rows of A are orthogonal, and this is also equivalent to saying that the columns of A are orthonormal, because the product with itself is 1. So rows of A are orthonormal and the columns of A are also orthonormal. Right? So these three statements are equivalent. This means that if I ask you to show that, if I give you a matrix and ask you to show that this matrix is orthogonal, then you can show that the rows of this matrix are orthonormal. If you show this, then immediately you can say that the matrix A is orthogonal. Or you can say that the columns of A are orthonormal. Then also you can immediately say that A is orthogonal. Fine? Okay. So now you have one homework here. You can try it home. Now the next definition is the normal matrix. So we have a real square matrix. This matrix is said to be normal if A transpose A is equal to A into A transpose is equal to A transpose A. Then we say that the matrix is normal. So from here we can, from the definition, it is immediately clear that every square matrix is a normal matrix. Sorry, every symmetric matrix is a normal matrix, because if you have symmetric matrix, then A transpose will be equal to A, and from here you can immediately say that A transpose is equal to A into A, which is A square, and A square is A transpose A. Okay, so every symmetric matrix is normal. Similarly, orthogonal matrix is also normal. You can see from the definition. In orthogonal matrix, we have just seen that A into A transpose is equal to A transpose A. Right, so it is a normal matrix, and the skew symmetric matrix is also normal. Okay, so that also you can easily prove. And then we have in the next point we have this as the normal matrix, because if we take A into A transpose, we get this one, and this is same as A transpose A. Okay, so this is again a very simple definition, normal matrix. Now we go to, so up to now we discussed whatever matrices we have discussed, all these matrices were real matrices. When I say real matrices, this means that the element of this these matrices are real numbers. Now, if the element, if one or more than one element of a matrix are complex number, then this matrix is known as complex matrix. Okay, so next definition is complex matrix. So A is said to be a complex matrix if entries of matrix are complex numbers. Okay.
Sir,
Yes.
is it necessary that every element is a complex matrix? Every element is complex.
No, it's not necessary.
Or if any one is, then it is a complex matrix also.
Yes. Anyone is complex, because if you have real number can also be treated as complex number. So if you write 2 is a real number. Basically, 2 is 2 plus 0 into I. Okay, so if you have even single entries, you can say that this is a complex matrix.
Okay, sir.
Okay, so for the complex matrix, we can define the conjugate of A as by taking the conjugate of each of the element. For example, if I have this matrix, okay, and I want to define the conjugate of this matrix. So then the conjugate of this matrix will be, you consider each and every element. So A bar, which is the conjugate of A, you consider the first element, write down the conjugate. Conjugate is 2 minus 8i. The second element, conjugate is 5 plus 3i. Third element, conjugate is 4 plus 7i. Next is 6i, so minus 6i. Next is 1 minus 4i, its conjugate is 1 plus 4i. And next is 3 plus 2i, its conjugate is 3 minus 2i. Okay, so this is conjugate of A. So this is the first definition, so first sub point here. Now the transpose of the conjugate. Transpose of the conjugate is known as conjugate transpose. So this is my conjugate matrix. And if I take the transpose, this is A star. So transpose of this is denoted by A star. So this is conjugate transpose of A. A star is conjugate transpose of A. So if you take the transpose, then the first row of A will become the first column. First row of A is this one. This becomes the first column. And the second row of A is this. This becomes the second column of A. Fine. So this is conjugate transpose. All right. So we have so we have this two definitions. So we have complex matrix. Then the conjugate of A is defined by taking the conjugate of every element. And the conjugate transpose of A is defined by taking the transpose of the conjugate of A. We denote A bar as the conjugate of A and A star as the conjugate transpose. Conjugate transpose of A. Now, for this we have the following properties. you have A star and star of A. This will be equal to A. So from here, if you just consider this example, from here you can see that this holds. So in general, this holds because if you take the star of A, if you take further star, that means first you make the conjugate and then you take the star. So conjugate of this will be, so A star and star of A will be, you take the conjugate here, so 2 plus 8i, 5 minus 3i, 4 minus 7i, 6i, 1 minus 4i, 3 plus 2i, and then transpose. Transpose of this will be, first column will become first row, 2 plus 8i, 5 minus 3i, 4 minus 7i, 6i, 1 minus 4i, 3 plus 2i. And this is same as the matrix A. Okay, so A conjugate transpose of the conjugate transpose is the matrix A. So basically this works like the transpose of the matrix. Now you have A plus B, conjugate transpose of A plus B will be equal to conjugate transpose of A plus conjugate transpose of B. And the proof is very straightforward. You just take the some general form of the matrix and then you can prove it. The third property is K times A, conjugate transpose of K times A is equal to conjugate of K, conjugate transpose of K times A is equal to conjugate of K times conjugate transpose of A. And the last property is conjugate transpose of the product AB is equal to the conjugate transpose of B multiplied by the conjugate transpose of A. Okay, so the proof is similar to the transpose of. So basically, conjugate transpose, we have a matrix, we have transpose of a matrix. This is for the real matrices. For the complex matrices, the corresponding concept is conjugate transpose. That's all. So all the proofs that you have done for the transpose, all these proofs will hold here. Okay, so these proofs you can try at home. You take any general form of the matrix and then you can show that all these proofs hold. If you feel difficulty, then you can ask me. Okay, I think the time is already over. So I should stop here and then we can discuss this. And in next lecture, we can start the next topic. But if you have any question, you can ask me. No question?
No, sir.
No, sir.
Okay, so I have to fix, in fact, 2 lectures now because one I was little bit ill on that day. So for that, I have to fix 1 lecture, and the other lecture I think we lost one Saturday. So 2 lectures I have to fix. Can we do it tomorrow?
So we lost 1 lecture and 1 tutorial actually.
1 lecture, 1 tutorial.
Yes, sir.
No, Saturday I think we lost 1 lecture.
Yes, sir.
In fact, the first lecture we could not do anything because we were setting up the things. And then second lecture also, I think we moved to MS Team, and then there was some delay in starting the lecture. So I will prefer to have two more lectures, extra lectures,
Oh, okay. All right, sir.
so that because I'm also going a little bit slow, so that everybody can understand. So if I go slow, then needs little bit extra time. So are you available tomorrow? Tomorrow morning we can do.
Yes, sir.
At what
So
time?
when we need to submit our assignments?
Today is Friday. Today is Saturday. So preferably by tomorrow.
So do we need to solve all the questions now?
I think in assignment 1 everything is covered. I don't think anything is left
Okay.
in assignment 1, because we are about to start this eigenvalue. Only this last topic is left, is Hermitian and skew Hermitian, which is same as symmetric and skew symmetric matrix. So even if you have some question on that, you can easily do that.
Okay, sir.
So shall we say tomorrow?
सर संडे को क्लास नहीं है ना?
Sorry.
सर संडे को क्लास नहीं है ना?
I think we can have 2 lectures tomorrow. Shall we say 10 o'clock tomorrow? कल 10 बजे ठीक है? 10 11 सॉरी, तो 1 घंटे का कर लेते हैं कल फिर, ठीक है?
Yes sir, yes sir.
Timing?
It is better.
Timing?
Yes, sir.
Timing 10:30.
How can I submit the assignment?
बिल्कुल सर.
Sir, we have a psychology tutorial from 11:05. So it will be better if it's from 10.
10, okay. So we can start from 10 to 11.
Yes, sir.
Okay.
Yes,
So
sir.
I'll see you tomorrow then.
Also, sir, how do we submit the assignment?
You can send it by email.
Okay, sir.
So what is the deadline?
Okay, so when you submit the assignment, you only S3 group should send the assignment to me. Other
Only?
group, only I'm taking S3 tutorial, right?
Yes,
So
sir.
you have to send your assignment to the tutorial teacher, not to me. So if I am your tutorial teacher, then you send me the assignment. So that means
Oh, okay.
only
Okay, sir,
S3.
because we missed our yesterday's tutorial. We had it maths tutorial yesterday and we missed it.
You missed it.
Sir, it is on Tuesday. Ab.
Yeah,
No.
yes, sir said that he'll be taking it on Tuesday.
Okay, so you have to send the assignment to your tutorial teacher, not to me.
Okay, sir, then we'll contact him.
Yes.
Okay. Thank you,
Yeah.
sir.
So
Okay.
for S deadline is
आज कल तक भेज दो, मंडे तक भेज दो, कोई प्रॉब्लम। अगर तुम्हें लग रहा है कि तुम नहीं कर पा रहे हो तो बेसिकली जो ट्यूटोरियल का डेडलाइन है ना, वो तुम्हारे ट्यूटोरियल टीचर ही सेट करेंगे।
okay, sir. Kal.
From lecture point of view, we are finished with all the topics that
Yes,
you
sir.
require to solve assignment sheet 1.
Okay, sir.
So I am expecting that everybody should be able to solve the questions by tomorrow, because you're also working, you're not stopping. अगर तुम कल सुबह स्टार्ट की होगे तब तो तुम्हें दिक्कत हो जाएगी, लेकिन अगर तुम जैसे जैसे क्लासेस चल रही है वैसे वैसे तुम अगर सॉल्व कर रहे हो ट्यूटोरियल, तो फिर मैं एक्सपेक्ट करता हूँ कि तुम कल तक कर लोगे।
Yeah, sure.
ठीक है?
Yes.
तो अगर कल तक कर लोगे तो मुझे S3 वाले बैच मुझे भेज सकते हैं।
सर मतलब कल क्लास है ना सर हमारी 10:30 पर।
10 बजे।
Yes sir.
10 बजे।
That question related to row reduced form.
Sorry?
Sir, I have a question related to row reduced form.
Row reduced form, हाँ बोलो। Vinas?
In criteria in row reduced form, that one in a lower row should appear to the right in the upper group.
Your voice is very low. Can you speak a little bit louder?
So I was saying that in row reduced form, is there any criteria that the first entry, one in a lower row, appear to the right of the one in the upper row?
Criteria means what? You have to apply the elementary row operations to get this in this form.
No, sir. Like in row echelon form, we have the criteria that the one should be to the right of the one in the upper group. Like it should be not in the same column one. It should
Yes.
appear in the column. So we have that criteria in row reduced form as well.
Yes.
Okay, sir.
You have this definition here. Where is the definition? Yeah.
So here it is not written that criteria, but I think there should.
Yes, sir. Only for row echelon form it was written.
Each column of A which contains the leading non-zero. So it is clear from the second point. Each column of A which contains the leading non-zero entry of some row has all its entries as zero. You cannot have one here.
Yes, sir, but
it will not be satisfied. For example, if this is my first element, I start from row 1, and row 1 has the first element as non-zero element as 1, then all the elements below in this column should be 0.
yes, sir, but in D part, if I just exchange row 1 and row 2, then still it will satisfy the first and second criteria, but I don't think it is then unique because I have got 2 row reduced forms.
Yes. Then it is fine. That is also fine. So that condition is not needed.
Yes, sir.
Yeah, so that is fine.
Sir,
So
but
we
for
don't.
row echelon form, it should be the right side of the one, right? Okay.
So that criteria is not applicable here in row reduce.
Yes. That is
So
not
then
applicable.
it will not be.
Usually when you form, when you start doing the row operations, usually you stop at this point and then do not interchange anything because you already have this criteria. So in most of the cases, you'll end up in this form. But obviously, if you interchange first row and second row, or maybe the other 2 rows, any 2 rows, then still you have this row reduced form.
Okay, sir.
Yeah.
Sir, then how the note is valid?
How?
That the row reduced form is unique.
Uniqueness in the sense like the row reduced form is. I will check this. Does not seem correct. I'll check this and I'll come back to you.
Okay, sir.
Any more question?
Sir, is there a proof that for any given 2 row equivalent matrix, they will have the same row reduced form always?
Sorry, what did you say?
Any 2 row equivalent matrix will always have the same row reduced form always.
So this is related to the uniqueness question. So I will expect that you can go to the same matrix by using the transformation.
Yes, sir, but we can always not go like that and do something other way and get a different row reduced form, like we pointed out.
Yes. So as I said, let me check this again, and then I'll come back to you whether how this uniqueness is defined there.
Yes, sir, please.
Yeah. Any more question? So shall I close this session now? If you don't have any question, then
Yes, sir.
I close this session.
Thank
Yes, sir.
Okay. Thank you so much, and I'll see you tomorrow.
Have a great time, sir. Have a
You
great time,
also.
sir.
You also. Thank you. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
you.
Thank you, sir.